Hello ladies and gentlemen, welcome to my lecture series Modern Gauge Theory. This is lecture 4, Young-Mills fields. Last time we were talking about the electromagnetic gauge field that was an U1 gauge group, an Abelian group, and now we generalize that to non-Abelian gauge groups, for example SU2.
At first, we want to look at some important group theory. We have unitary operators U1, SU2, SU3 and others. And these are exponential functions. We have used U1 operator to describe the electromagnetic interaction in the last chapter. And here we have seen there is a scalar factor in the exponent of the unitary operator here. And if we multiply two operators, then this product is commutative. Though we talk about an Abelian group, it makes no difference in which order we multiply. Now we have a small calculation to that. This is a U1 operator with a scalar lambda here in the exponent. And if we use the first two terms of a Taylor expansion, then we have 1 plus IE lambda. If we multiply a wave function psi, then we have the structure, wave function plus the change, is the new wave function. So if we multiply two U1 operators here, then we have two exponential functions, or then the terms of the Taylor series. And then if we solve the parentheses here, we get this expression here, 155. Here we have the multiplication of the lambda parameters. Okay, these are scalars, so the order makes no difference. If we consider SU2 operators, special unitary group of two parameters, we have matrices in the exponent. And so if we multiply two operators here, then the product is not commutative. It makes a difference in which order we multiply. And so we talk about a non-Abelian group. Here we make the same calculation. Now we have a unitary operator again, and here we have the tau matrices. These are the Pauli matrices that should be known from the elementary lectures in quantum physics. We use the tau matrices to describe, for example, the electron spin. And if we look at the first two terms of the Taylor series, then we have 1 plus, and here this part. And then we multiply two operators here. Then we have two exponential functions here. Then the terms of the Taylor series. And then we solve the parentheses again. And then we have here in the last term of 157 two Pauli matrices, tau. In some other literature, the symbol sigma, a small Greek sigma, is used to denote the Pauli matrices. We use here tau. We call the matrices tau here the generators of the group, the SU2 group, transformation group. We can write down a commutator for these matrices. That's this equation here, 158. The epsilon coefficients are called the structure constants of the group. It is the so-called Levi-Civita symbol. Here we have the Pauli matrices, tau 1, tau 2, tau 3, that should be known. And of course we talk about a group, we must have a neutral element, that is the unit matrix here, usually written with index 0, tau 0. Each Pauli matrix is its own inverse element. A general unitary group, UN, includes all n times n unitary matrices. If we have n is 1, then the matrix is reduced to a scalar, a single value, what we have seen in U1. Then a special unitary group includes all n times n unitary matrices, and those form a Lie group. And here special means that the matrices have gotten determinant value of 1. And because of this additional condition, the dimension of such a group is not n squared, but n squared minus 1. So in case of SU3, we have a dimension of 8, and here we have the 8 Gelman matrices. They're usually denoted by a small Greek lambda. And here we have the generators T, and they're defined by the Gelman matrices divided by 2. Here again we can write down the commutator with the generators T, or we can write the commutator with the Gelman matrices here. Here the F factors are the structure constants, and the non-vanishing ones are written down here. Others are 0. Now we introduce the isospin. If we look at the elementary particles, then we find some groups which have nearly the same mass but different electrical charges. Examples are the proton and neutron, or the 3 pi mesons, and others. And though we suppose now that we have only different states of the same particle. If we talk about protons and neutrons, we talk about a nucleon. A nucleon can have 2 states, the proton and the neutron state. Others are, for example, up and down quark, or the K mesons, kaons, or the pi mesons, pions. Here we have 3 particles. Here we write that like a spinor. It is mathematically similar to the spin of the particles, but it hasn't anything to do with the spin. So it is a new degree of freedom, and so we call it not spin but isospin. Werner Heisenberg introduced the notation of those spinors. If we consider the interaction of nucleons, we consider the nucleus of an atom. So normally the nucleus of an atom must explode because of the same positive charge of the protons. But obviously an atom is stable, so there must be another force which keeps the nucleus together. And so we call that force the strong force, or the strong interaction. This strong interaction is equal between all nucleons, or we can say baryons or hadrons, and it hasn't anything to do with the electrical charge. So we have to consider that apart from the electromagnetic interaction. And further, if we look at some particle processes, we find that there is another kind of interaction in which are especially leptons like electrons and neutrinos are involved. That force is obviously weaker than the electromagnetic or the strong one, and so it is called the weak interaction or the weak force. Now we continue in analogy to the electromagnetic interaction. That means we need a transformation operator to transform the wave function psi 165 here, because of the fact that we have spinors. That means a kind of vector, we can say. So we need a matrix to transform it. And so in the operators of the SU2 group, we find the Pauli matrices here, with division by 2, and an arbitrary parameter alpha. Here we have written vector arrows onto the symbols because SU2 means we have 2 squared minus 1, 3 dimensions. These 3 dimensions are given by the 3 Pauli matrices. And so we also have 3 parameters for the 3 dimensions. And so we write here vectors. But this inner space, this 3-dimensional isospin space, hasn't anything to do with our normal space around us. Again, we use the first 2 terms of the Taylor series. So we have here the unit matrix multiplied by the wave function, that's the original wave function, plus the change of the wave function. And that is the new wave function, the transformed one. So we substitute that in the Noether theorem. Now here we have for the capital Y, here our new transformation. We substitute that in the Noether current, here 168. Then we get here 169. The small y is vanishing because we haven't got any transformations in the space-time coordinates. And we write a plus hc, the hermetically conjugated term. So the complete Noether isospin current is then here 170. Here we have written out the hermetically conjugated term. In the Pauli matrix, there isn't got a plus here because the adjungated matrix is a matrix itself. Because we have a 2-component spinor, then the index I here runs from 1 to 2. If we consider a scalar field with a known Lagrangian here, 171, then we would get for the isospin current here 172. The mass term is vanishing because we differentiate with respect to the derivatives of the wave functions. And so we get only terms from the first addend here. We have to cancel one differentiation here out, and then one differentiation stays here in the 2 addends. If we have spin a half spinors, then we have for the Lagrangian this one, 173. This leads then to the current here 174. Psi bar stays as a factor. Then we have to write down here the summation index nu, which is not written here in this version of the Lagrangian. Then we consider the variation of the Lagrangian. In the Lagrange density function we have of course the wave functions and the derivatives of the wave functions as the independent variables. We use the SU2 transformation. In general, we have to differentiate with respect to all the independent variables and write to every differential quotient the variation delta 176. Then we have for the variations these two expressions here. Delta psi is I alpha tau half psi, and the derivative, of course. Here the only difference between the variation of the wave function and the variation of the derivative is that we have here the derivative of psi. Then we substitute the variations in 176 and get 178. Then we can factor out I alpha is in each ident here, or we can divide by I alpha, and so this big sum here must vanish, must be 0, 179. In analogy to the U1 group, we have to consider now a local gauge transformation. That means, we have the parameter lambda here, which is dependent on the space-time coordinates. So we have now in the unitary operator here the parameter lambda, vector, and tau half, the same like before. Now we can write for the transformation, we use the Taylor series again with the first two terms. Or for the hermetically conjugated version, we have this here, 181. Then we have written here factor G. In the electromagnetic interaction, we had written E for the elementary charge. But here we don't know which factor it should be, though we write a general factor G. If we consider a global transformation, then we have no problems. But if we transform with a local transformation, then we will get some problems. So we consider here the derivative of the field. That means, we apply the unitary operator to the derivative of the wave function. Because of the space dependence on lambda, we get an additional term here, with the derivative of the parameter lambda here. Or for the hermetically conjugated one, 183. Okay, we have for the normal variation of the wave function these two equations here, 184. And for the variations of the derivatives, we have here these two equations here, 185. Then it must be that the variation of the Lagrange density must vanish. If we substitute now the variations here, we get here this equation 187. The problem is now, we have here an additional term. So the variation of the Lagrange density would not vanish. So in analogy to the electromagnetic field, we introduce a covariant derivative. We will do that in full analogy. We have the partial derivative and we add a term with a gauge field here. But in this case, we have a three-dimensional isospin space. And so we multiply here with a matrix, and that means that we have not only a mu, but we have another vector for three components in the isospin space. We could say that the a mu is a 4 times 3 component quantity. The hermetically conjugated version here. Then again, the transformation of the derivative must be of the same shape like the normal derivative. Here 189. Now we write down the transformed derivative of psi here, but now the covariant derivative, not the simple partial derivative. We have the transformed covariant derivative, so we have here in the parentheses a prime, that the transformed gauge field. Here the transformed psi, that is a unitary operator applied to psi. On the other side, here we have the unitary operator, this, and then we have the covariant derivative here, that is here the parentheses, that applied to psi here. Now we solve the parentheses here. The partial derivative is applied to u psi. That means we have to apply the product rule of differentiation. Though here in this term we differentiate u, and in the second term we differentiate psi. And here we must be careful with the order. We may not change the order of the unitary operator and the psi. And then the last term is the term with the gauge field and u psi. That's this one. Then on the other side we have u partial derivative psi, that is this term here. And we have u, the term with a gauge field psi, that is here the last addend. We can write Ig in front of the other things because these are scalar factors. We can cancel out an identical term on the left and right side of the equation in 191. We have here unitary operator and the derivative of psi. And here we have the same unitary operator, derivative of psi. And we write the equation so that the transformed gauge field is on the left hand side of the equation here, because we want to know the transformation rule of the gauge field. Though we have 192, then we cancel out the wave function psi. Then we have a pure operator equation, and we multiply by the inverse operator, means u exponent minus 1, and we divide by I, the imaginary unit. So we have then here 193, then we have here no psi and no u on the left side here. Then here the first term on the right side, there is now an inverse operator on the right side of the term here. And then for the last term here, we have the derivative of u. Then we use the following equation. That's the same what we had in the electromagnetic interaction. This term is equal to this term. We can see that if we use the following small calculation, if we have u and inverse u, then that's the unit matrix. Then we differentiate on both sides. So we have the differentiation of u minus 1, and here the differentiation of the unit matrix. The differentiation of the unit matrix is vanishing because that's a constant. And then because of the product rule of differentiation, we have the two terms here, the derivative applied to u plus the derivative applied to the inverse operator. And though this is equal to this, but we have then another sign, because if we write here the term on the other side, then it would have a minus. So we can then cancel out on the right side the unitary operator here at the left side, and the inverse operator at the right side here. Yeah, we consider an infinitesimal transformation, and though we can use for the unitary operators, again, the Taylor series with the first two addends. So we write here for the unitary operator 1 plus the term with the parameter, and here it's the inverse, so we have here 1 minus I and so on. Then we solve the parentheses here on the right side. So we have 2, 2 and 2 terms, means we would get 8 addends. And so here we have these 8 terms. Okay, I don't explain that now in detail. That is a simple algebra. You have only to solve the parentheses, and yet then you get the 8 terms. But then if we look at the terms here, we see here is the derivative of the unit matrix, and here. So these two terms vanish. And then further we divide by a factor g, because we have g here in all terms. So we get here equation 197. Here we look at the great parenthesis. The tau matrices are constants. So the derivative is only applied to the parameter lambda. Yeah, here we needn't to write the parentheses, only factors, but we have to keep the right order. And here also we only write the term without the parentheses. And here in the last term again we have the situation that the derivative is only applied to lambda because the other factor is a constant. And though we have 198, and here we introduce a new vector, a, small a. If we look at the terms here in 198, then we see that this term is the same term like this, but a and lambda are exchanged and the sign is different. So that means we could write that as a commutator here. And we write the last term here to the definition of the a vector here. Then we can write transformed gauge field here is the old gauge field minus this term plus the new defined a vector. Then we multiply by 2 and the inverse tau matrices from the right. So we have this equation 200. Then we suppose that the lambda parameter is infinitesimal small. And so we have here in the second part of the a vector 2 lambdas. We can neglect this term then. And we write instead of the vector arrow now indices, alpha, beta, gamma, and so on. Yeah, that means we write for a this. Then we have for the transformation of the gauge field, here 202. We have for the transformed new gauge field, the old one, then minus the derivative of the parameter lambda. That is the same that we had in the electromagnetic case. But here we have an additional term, this vector product as an additional term. Now we look at the gauge field. Like in the electromagnetic case, now we need an additional term in the Lagrangian for the gauge field alone. And in analogy to the electromagnetic interaction, we define the following commutator and the field tensor F here. Because of the isospin space, we have here a factor with the Pauli matrix tau. because in the covariant derivatives we have the same matrices. We write out the commutator here. So we get here this longer term. And now we solve the parentheses here. So that means, we get here 2 times 2, 4 addends, and here the same with a minus sign, 2 times 2, 4 addends here. And the operators must be applied to something. So we write here the neutral element, the unit operator, unit matrix. The same have we got here in the third terms. So here we write also the unit matrix. Now we can cancel out some terms. This term is the same like this. The differentiation of a constant is 0. So these 2 terms and these 2 terms vanish. And so we have only these 4 terms in 206, and we have written that without the great brackets here. We have multiplied I and G to every addend here. Okay, I think I needn't to explain that. I and I here is a minus, and G divided by G is 1. So we have here minus this term, for example, here, and so on. Then we write the terms in another order. We write this positive term with the derivative of A first, and then we write this one. And we do the same for the other 2 terms, the positive first and the negative after the first. Then we can write in 208, we can use parentheses, we can factor out tau half, and here we can factor out the components of the gauge field, because the single components of the gauge field are scalars. And so we can write the scalars here outside the parentheses. And in the parentheses, of course, we have these 2 tau matrices with a half and these 2 tau matrices here. Then we use that the commutator of 2 tau matrices is 2 imaginary unit, Levi Civita symbol, and the third tau matrix. That should be clear from the elementary lectures in quantum mechanics. So we can write now in the last term here for this term with the Pauli matrices. We can factor out a quarter, we can say, and then we have this expression, and we have 2 divided by 4 means we have a division by 2. Here we have the division by 2 of the new matrix tau I here. Then we can cancel out the term with the tau divided by 2 here, because in every addend we have the same term. We need to write here the parentheses, and so we have this 210. This is now the result for our field tensor F. So we see that it is the same like in the electromagnetic case, but here then plus G epsilon dot. We have an additional term here with a vector product. This is an additional term that we hadn't got in the electromagnetic case. Or we can write instead of 210, 211 with the vector symbols here. So we don't use an index I for the vector in the isospin. We use vector arrow for the vector in the isospin space. To avoid writing tau half permanently, then we use this abbreviation F tilde, means F is multiplied by tau half. So we can write for 209 here, where we have the tau matrices in the terms. We can write now this 213. f tiled is then a tiled twice here. Then in 202 we see that the variation of the gauge field A is minus the derivative of the parameter lambda and then the term with the vector product of the parameter with the vector product. So we can write for delta A this, or with tiled this. Then for the variation of the field tensor F, we can write directly that from 213. So the variation of F is variation of the first term. So we have here delta variation and differentiation are computable. Here we have the variation of the second term. And here in the third term we have twice the A. And that means here in the first term we vary the first A, and here in the second term of 215 we vary the second A. This can be written like 216. This is an exercise for students. Show that 216 follows from 215. That's not so complicated. You only need to solve the commutators here, and then you substitute the variations of the gauge field delta A, and then it's a straightforward algebraical calculation, and then you will get 216 for the variation of the field tensor F. The next derivation is more complicated, so I will show it here. We want to simplify 216, and we use 213 as the expression for F. And so we can write for the difference of these two derivatives, we can use F plus the term with the scalar product or with the commutator here. And so we have here in the first commutator lambda, and then here as a new term F plus this commutator with the variables of the gauge field. Then we use the calculation rules for commutators. That should be clear. We have here a sum in the second part here in this commutator. That means I can write that in two commutators. In the first we have lambda with the first addend here, and in the second part we have here lambda with the second addend here. The third term stays like it is here. Then we can factor out here the factors I and g, and though I and I is -1 and g squared, and we exchange these two a's, a mu and a mu. That means we would get another minus, and minus is then again plus here. We see now that the second and third term here are identical, but they have different signs, plus and here minus. And so in 219 we can cancel out the last two terms, and the only term which stays in the equation is here the first commutator lambda f. So we write for the commutator this. That means we write instead of the tiled the Pauli matrices here into the equation. And here again, the components here of f and lambda are scalars. We can factor out them. And then we have here commutator of Pauli matrices. And so we again use this equation, which we used above. And so we can factor out a quarter first perhaps, because we have here factor 2 means 2 divided by 4, it's here a factor a half, and instead of the 4 taus here we get only 1 tau k here. Then we have here I, and here another I that is -1 here. Okay, that's no problem to understand. So we have 222, and we can cancel out tau half, and so we have this short term for the variation of the field tensor f. we can write for the transformation of f, the delta f is only the new transformed f prime here, minus the old one, minus f without prime. And we write the f here with a positive sign to the other side of the equation. And so we have here the transformation rule for the field tensor f here in the Young-Mills theory. In the electromagnetic case, the field tensor f was invariant under a U1 gauge transformation. But here, under a SU2 transformation, f obviously is not invariant. Yeah, we have again this additional term here. Now we look at the Euler-Lagrange equations. We have introduced the gauge field A, like in the electromagnetic case, and that means we need an additional part for the Lagrange density function. Yeah, we try the same like in the electromagnetic case and write for the Young-Mills Lagrangian here minus a quarter f covariant and contravariant. That means we have here a double scalar product. And here we have an additional index I for the isospin. Yeah, and of course this term must be gauge invariant. Yeah, we look at the following calculation. We write down the trace of the scalar product of the two f tensors. Here written with tilde, that means we have the factor tau half. The single components of f are scalars, and so we can factor out the two f factors here, and we have the trace of the Pauli matrices. A Pauli matrix is its own inverse. That means here we get the unit matrix. And if we want to calculate the trace now, yeah, we have here unit matrix 2 times 2 matrix. In the diagonal we have 1 plus 1 makes 2. 2 quarter are a half here. If we compare now this term 226 with the term 225, we see the only difference is a factor minus a half. And so we can write for the Lagrangian here minus a half and trace of the scalar product of the two f tensors. Here we want to look at the transformation behavior. So we vary the Lagrangian, delta L here. Here we have two factors. That means if we vary, we get to a dense. So here we have the variation of the first factor f and here of the second factor f. Then we can substitute the variations. We had here the variation of f, and then we substitute that. Then we get here this here, 229. And then we see that the left and the right term are identical. And here we have tau multiplied by itself means unit matrix. The trace is 2. So we have here as the factors a half plus the same here, half is 1. And so we have now number factor. We have the minus a half here in front. And so we get this expression here, 230. And here the variation must be 0. If we look at this term, what have we got here? We have here epsilon tensor, Levi-Civita symbol. This symbol is unequal 0 if the three indices have different values. If two values are equal, then epsilon is 0. Then we have here the two f factors field tensors with indices for the isospin j and k. That means only if these two indices are equal, we get a value unequal 0. Yeah, and so the whole term is 0. And then we have for the Young-Mills gauge field, together with an isospin field psi, this Lagrange density function here, that's the same like in the electromagnetic case. Then we get the Euler-Lagrange equations if we make a variation calculation with the Lagrange density function. So if we vary with respect to psi plus and d psi plus, then we get this. Yeah, this is an exercise for students. We have executed such a variation calculation several times. And for the hermetically conjugated, here we have 233. And for the gauge field, we have this equation here, 234. They've got the same structure. And here we have this equation. It is again the same like in the electromagnetic case, but we have the additional index here for the isospin. And so in full analogy to the U1 gauge theory, we have for the current this. Yeah, the only difference is the isospin component here. Yeah, here we have not the elementary charge as a factor. Here we have the general factor G. And now we want to calculate here the differential quotient to determine the current J. The Lagrange density does not depend directly on the gauge field A. The gauge field is included in the field tensor F and in the covariant derivative. So we apply here the chain rule of differentiation, and we must apply the chain rule to all the independent variables in which A is contained. It is contained in the covariant derivative, so we have here this first term, the hermetically conjugated term, and we have F. A is contained in F, and so we have here the chain rule with the field tensor. So we calculate the first part. So we have here these two differential quotients. We substitute the covariant derivative d here. Then we use the metric tensor to change this contravariant index into covariant index. Then we have here the same A with the same indices like here. So if we differentiate now, this factor is cancelled out. Yeah, here we have in the first addend the derivative of psi. The derivative of psi does not depend on A. So this first addend is vanishing. And so here we have then the factors, yes, Ig, G mu nu, tau half, and psi. Yeah, we write the constants I and G here in front. Then, this is the result here for this term, 241. I needn't to show that for the hermetically conjugated term, that is exactly the same calculation. Factors are exchanged because of the difference between a column and a row vector, but that is basic linear algebra, that's no problem. Then the last term here, we substitute L, that is minus a quarter FF here. And here in the second differential quotient, we substitute F by this, what we had, the ADA and the additional term with a vector product here. And then here we factor out minus a quarter. And then here we have a product of two terms, of two factors, which depend on F. So we get here two addends. The first F, A beta, that's the same like this F here. The only difference is here we have index J and here I. So we must write delta Ij, and yeah, the second F factor stays here. Then in the other part here we differentiate the second F. The first F stays as a factor. Then yeah, we write the differential quotient here. Then we use the metric tensor here to make out of these two covariant indices contravariant indices, mu here. In the second part we do the same. We use the metric tensor to change these contravariant indices into covariant indices at the gauge field here. Then here in the next line, that's a mistake here, that must be quarter, not eighth here. Okay, this delta means only that this I changes into a J. Then here we write two Kronecker symbols, deltas, to change the mu and nu, change the alpha and beta index into a mu and nu index. Then here the first derivative of A and A itself are independent variables. And that means that this first term and the second term vanish. So we have only this term here. And here we have again the product of two A's. That means we get two addends here. So we differentiate this A. We have here mu k. And we have here mu I. So we write delta ik here. And in the second term we have a mu L, mu I. So we have here delta IL. Then we factor out a G here. And here this and this is the same. But you have J and I, that is delta Ij. And the other two deltas are used to change the alpha beta index here into mu indices. Then here we can factor out the two metric tensors G here. And then we have two addends here in the parentheses. Then we multiply these two G tensors with this F tensor here. So we get this Fj nu contravariant. Here we have, because of the delta Ij instead of I, a J. And the other four G tensors vanish because that would only be a unit tensor, neutral element of the multiplication. Here we have changed the k into I because of the Kronecker delta here. And the same here in the other term. We have changed L into I. So here we have twice the same. That means we can write 2 Fj mu nu. Yeah, these two terms are also the same. So we have another factor 2, means a factor 4. This cancels out the factor quarter here. And now we get this. So this is the result of the last part here. then we obtain for the isospin current J, this expression here, 248. Here we have the additional term here in this case compared to the electromagnetic case where we hadn't got such a term here. The transformation law for the current, that's here 249. Exercise for students show that 249 is the correct transformation rule for J. And for the energy momentum tensor, for example, we had in the Noether theorem here this. And so we can write now in analogy here this. And another remark, for the covariant derivative there is a Bianchi identity. That means we can write this with the double commutators. We have executed the Yang-Mills theory for two-component spinors, and we have used the 2x2 Pauli matrices. But the question is, what must we do if we have, for example, an isospin triplet? For example, pi mesons. There are 3 states of the pi meson. The negative one, the neutral one, and the positive one. We have isospin value 1 with the 3 values, isospin values -1, 0, 1. And so we need 3 times 3 matrices instead of the Pauli matrices. Okay, what we can say is the I3 matrix must have the eigenvalues of the 3 states for the isospin. And so we can write here in the diagonal the isospin values of the 3 pi particles. 1, 0, -1. And then we must determine the operators I1 and I2. To do this, we consider the ladder operators. That should be known from the basic lectures in quantum mechanics. The ladder operators. I plus is I1 plus I2. And I minus is I1 minus I2. Then we can apply the ladder operators to our pi states. If we apply the I plus operator to the pi minus state, then we have I plus, and the I minus isospin vector is 0, 0, 1. And then we must get the next higher state, that means the neutral pi meson. Then we have 0, 1, 0. Square root 2, that's a normalization factor. If we apply then the I plus operator to the pi 0 state, then we get 1, 0, 0. That is the pi plus state then. And if we apply the I plus to the pi plus state, then we must have 0, 0, 0, 0 vector, because there is no state beyond the pi plus state. We can write in analogy these 3 equations for the I minus operator. And then we can write for the ladder operator, I plus is then normalization factor, and then we get this, because if we multiply here this vector with the second row, then we must get value 1 here. Or the 3 vectors here, are found here in the matrix 0, 0, 0, that's the first column. Then here 1, 0, 0, that's the second column. Or here 0, 1, 0, that's the third column here. And then, in complete analogy, exercise for students makes the same for the I minus operator. Then we get this matrix here. And now we can determine the I1 and I2 operator. We substitute I plus and I minus here in 253. Then we have two equations with two unknown quantities, I1, I2. And that is easy algebra. If you solve this system with two equations and two unknown quantities, then you get the result. Then I1 is then this matrix here, and I2 this matrix here, 256. Here we see in I2 that's the same like in the Pauli matrices. We have the imaginary unit I in the matrix. If we have isospin 3/2, that means we have a particle with 4 different states, for example delta baryon. Then we need 4 times 4 matrices, and we have then in I3 the values of the 4 states, plus 3/2, plus 1/2, minus 1/2, and minus 3/2. And then student exercise here with the same procedure like we have determined the operators here in the triplet case. Then you can determine here the operators in the case of isospin 3/2.
Now we finish lecture 4. Next time in lecture 5 we will talk about the weak interaction. Thank you for watching. See you next time. Goodbye.